right, so copper. Copper. Copper, 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 copper. Electron battleship. Where does copper end on? What is the last electron filled in? 3D9. So, if we draw out the orbital diagram, 1s, spin up, spin down, 2s, spin up, spin down, 2p, 1, 2, 3, spin up, spin up, spin up, down, 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 3s, spin up, spin down, 3p, spin up, spin up, spin up, down, 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 4s, spin up, spin down, 3d, 1, 2, 3, 4, 5, spin up, spin up, spin up, spin up, spin up, down, 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 and down. 3D9. It's a lot. But the point of today is all about the term stability. No, not stab. Stability. So, we are going to dive in to what we call the half-hole rule. And basically all this rule is your sublevels are more stable if they are halfway filled or if they are fully filled. Halfway filled or fully filled. Now, for most cases, we don't do anything dramatic with this rule. But there are a few exceptions on the periodic table where we actually will change our electron configuration in order for a more stable configuration to be in a more stable configuration. So, in this case, copper, how many electrons am I away from having a full 3D shell? One. One right here. But without adding an electron to the atom, how can I rearrange this in order to abide by this half-hole rule? Yeah. What if I take one from the 4s and transfer it over here to the 3D? Now 3D is completely full and more stable. What about 4s though? 4s is halfway filled. So in order to have both a halfway filled sublevel and a fully filled sublevel, yeah, I can break those three rules. I can break the rules of filling in electrons around the nucleus in order to have a more stable configuration. So, if I was to write out the full electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9, I would change my 4s to a 1, 4s1, 3d10. Or the noble gas configuration, nearest preceding noble gas to copper is argon, in brackets, and I would have 4s1, 3d10 as my electron configuration. That is the half-hole rule. Now, I'm going to require you to know 4 total exceptions to your electron configuration rules. Copper is one of these exceptions. What do you think the other ones are? Oops. There we go. So we have copper. You guys mentioned silver. Oops, that's not how you spell silver. What would be the electron configuration of silver?
1s2, 2s2, 2p6, 3s2, 3p6.
Start with 5.
Okay. 5s2.
5s. No. What's the exception? 5s, 1, 4d10. There's your exception. There's silver. 5s1, 4d10. All right, now you have 2 more exceptions. One is in the 3d. What is your other exception here in the 3d? So take a look at this. Take a look at this. Argon in brackets. 4s, 3d. So if I have my 4s2, 1, 2, 3, 4, 5, 4d, 1, 2, 3, 4. How close am I to being halfway filled? So if I move that electron, this represents chromium. What's the other exception I'm going to require you to know? Right below it, molybdenum. So your 4 exceptions are copper, silver, chromium, and molybdenum. Those are your 4 exceptions you need to know. Okay, now let's apply this. Let's apply this. Because again, we're not going to always dramatically change our electron configurations to abide by this half-hole rule, but the stability still exists within some of the trends that we've already discussed. Here is your trend on first ionization energy. What is first ionization energy?
It's the energy required to take off a electron.
The energy required to pull off an electron from a valence shell. So here, I'm going to look particularly at period 2 first ionization energies. Is this a linear trend?
No, that's not.
On average, yes. But what do you notice? You have some exceptions in period 2. Now, before, when we studied this, you guys didn't have the background information to really explain these trends. But let's go ahead and label this so that we can do a better job this round. So, what is this element? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So you see the trends occur between beryllium and boron, nitrogen and oxygen. Draw out your noble gas configurations for these 4 elements. Go. So let's do the orbital diagrams instead. So beryllium ends on what? 2s2. So spin up, spin down. Done. Boron ends on what? 2p1. So spin up, spin down, and 2s, and then 2p's. You have 1 electron in the first orbital. Now, if we pay attention to the half-hole rule, we're not actually going to change anything about these electron configurations. These are the electron configurations, but we're going to try to explain why it's easier to pull this electron off in comparison to this electron. So you see the last electron in boron. Why is it easier to pull that electron off in comparison to the last electron filled in for beryllium? Half-hole rule. How close are we to being a full sublevel?
50%.
We are 1 electron away. We are 1 electron away. Versus we have a full 2s. We are more stable with the full 2s and nothing in the 2p than we are with 2 electrons in the 2s and 1 electron in the 2p. So by pulling this electron off, we're actually more stable as beryllium's electron configuration than boron. So that's why we see this drop in the first ionization energy trend. What about with nitrogen and oxygen? Nitrogen ends on what? 2p3. What do you notice about 2p? It's half full. Oxygen, on the other hand, is 1 electron over being half filled. So this electron is easier to pull off than this one, as we see in our trend in our first ionization energies. So again, being halfway filled is more stable than being something other than halfway or fully filled. So again, we can use these concepts with electron configurations to go and explain some of the trends that we explored prior to this unit. And these trends will continue as we discuss and get into our unit on bonding as well. Questions?